My name is Doug Erwin. I'm a paleontologist from across the river. And I am actually the curator of the Burgess Shale, which I'll talk about. As it happens, I'm actually the curator of, I calculated this morning, 14% of all the specimens that we have at the Smithsonian. And the reason for that is actually not because I'm a good curator, it's because we have the worst personnel department in the federal government, and we keep losing people faster than we can hire them. And so everything gets dumped on who's ever still alive. But I'm going to talk about dead things, not live things. And I'm happiest in the interval between about 650 million years ago and 200 million years ago, when life was good. Politicians in Washington say life has been going downhill since, 10 years ago or however long. It's actually, since the last 200 million years, it's been straight downhill. But back when life was good, in the Cambrian, we have all sorts of wonderful things like Opabinia, which is in the middle there, which has got 5 eyes and the stalk proboscis out in front, and Anolocris, and that's actually one of the fossils of Opabinia, and Pikaia, which I'll mention up there in the upper right. And it's fun just to work on the Cambrian explosion, but this has also led famously to lots of questions about issues of contingency and determinism. And to what extent has the history of life been one that's driven simply by historical chance, not exactly chance, because chance is a slightly different issue, and to what extent have the features that we see in the history of life, either by comparative studies today or by looking at the historical record, been influenced by the sort of universals that are the topic of this discussion today. And famously, Steve Gould wrote this book, Wonderful Life, in 1989, in which he said that the whole reason we're here as chordates and humans is simply the luck of the draw that Pikaia, this little wormy thing that I showed you in a previous slide, which was one of the earliest cephalochordates, happened to survive the decimation that removed most of the weird wonders of the Cambrian explosion. And so in the usual Gouldian fashion, if Pikaia does not survive in the replay of life, we're wiped out of future history, all of us from shark to robin to orangutan. If you knew Steve, you can sort of imagine all this. And then he says, I don't think that any handicapper, given the Burgess evidence as known today, would have granted very favorable odds for the persistence of Pikaia, this cephalochordate. And the problem with Steve's, well, a couple of problems with his argument. But one of them is that, in fact, there were a whole bunch of vertebrates back there. In 1989, he only knew about Pikaia, but 4 years before in the Xinjiang in Yunnan province in China, where I was 2.5 weeks ago, actually, Chinese paleontologists discovered lots of other chordates and vertebrates. So, in fact, there were a far larger set of things that could have survived than just Pikaia. But that's a minor problem with the issues that Steve raised. But Steve really didn't care about the Burgess Shale. Steve cared about the question of what's the nature of history and what universals can we identify. But the issues that he raised in Wonderful Life have led to a long series of discussions by philosophers of science trying to establish what he actually meant by history and what different types of contingency there actually are. John Beatty wrote a famous paper in 2006. He's a philosopher of biology up at UBC in British Columbia, and he focused on sensitivity to initial conditions, the middle one there. But other philosophers have identified a series of other types of contingency that might have been operating in the Cambrian or in the history of life in general. And I've been working with John and a couple of other philosophers of biology in the last year or so, and what we've realized relatively recently in the last few months is that many of these issues are not unique to biology or to history in general, but affect all complex adaptive systems. And so I think this meeting that we're having right here and some of the other activities that SFI is already planning on engaging in are incredibly timely because they're addressing, I think, a fundamental issue for complex adaptive systems that those of us associated with SFI have been involved in or interested in for a long time, and which we've sort of been chewing around in various fashions for the last 3 decades, but in some ways haven't addressed in a very rigorous fashion. And I think it's really timely to start doing that and to start asking to what extent does contingency actually affect the outcome of these historical processes. And before I move on, I want to mention a couple other things. One is that one of the critiques of what Steve did was mounted first by another colleague of mine, Simon Conway Morris, who just retired from Cambridge, who's completely mad. He believes, quite honestly, he believes that the whole point of evolution is the Queen of England or the Church of England, probably the Queen of England too, we'll discuss that later, David. But Simon believes that the ubiquity of convergence, the fact that similar morphologies have repeatedly evolved over time, is a strong argument against the importance of contingency. And the argument between Simon and Steve has been wonderfully dissected in a forthcoming book by Russell Powell, who's a philosopher of biology at BU, coming out from MIT Press, called Contingency and Convergence. Russ was actually a lawyer at Skadden Arps in New York when he decided that there had to be a better way of making a living than being a lawyer at Skadden Arps in New York City, and he went back and got a PhD in philosophy. So I want to return to the issue of the Cambrian and continue along the lines that Carnita just raised. This is an evolutionary tree of the major groups of animals in black, so sponges and placozoans, and then deuterostomes and lophotrochozoans and arthropods and all up there. The 3 closest cousins, which have been studied intensively by groups in Barcelona and Berkeley recently. And then plotted here is the expansion of the regulatory capacity of the holozoans, the entire clade down here, and then successively the metazoans and other clades. As was just discussed, one of the things that's happened, particularly in the last 5 years, is that a lot of the essential tools of animals have turned out to have evolved long before animals. And this has some interesting implications for thinking about what the transition is between these other holozoan groups, things like choanoflagellates and ichthyosaurians and philastrians, and animals as a whole. And the argument that I've made in recent work is that this transition is less consequential than it seems because of extensive co-option that happens independently in different clades later on. But this raises the question about it raises 2 questions. One is that a lot of the apparent convergences that Simon harps on so much are what Russ Powell calls Gouldian repetitions. They're actually the parallel evolution of similar morphologies because of a shared genetic and developmental capacity. So they're not completely independent events. They're not like ichthyosaurs and something from another planet converging on a tuna-like morphology. And so that this very deep ancestry of much of these developmental toolkits places a very different view of how we look at convergence and determinism across the tree of life. And I'd like to suggest that although this is, because I'm a paleontologist and not really a theorist, although most of my paleontological colleagues think I'm a theorist, it raises a general question, I think, about history, which is how much of what we think of as being convergent patterns is actually, in fact, what Russell describes as these Gouldian repetitions because of very deep conservation of similar patterns. I think one of the issues that we need to address in trying to untangle this problem of contingency and convergence is the extent of this underlying common framework across adaptive systems that has produced similar results, so apparent universals that really rely on deep conservation of what may have been historically contingent events. Now, that said, when I was first, 2 years ago, I was talking about this in a course on gene regulatory networks that's taught at MBL every fall, and I mentioned that Arne Sevi-Pedres' work had shown that these things called distal enhancers first evolved at the base of Metazoa. And Ellen Rothenberg, who's a developmental biologist at Caltech, threw up her hands and she said, that's the answer. That's the origin of animals. Get distal enhancers and everything else follows from that. And that, if you are into gene regulatory networks, you'd understand more about why she threw up her hands. But the interesting thing is that you can make an argument that this historically contingent event of this new kind of regulation arose at the base of Metazoa, and that led to animals. And that sounds like this sort of one-off event, like the origin of the eukaryotic cell. But it turns out that there's unpublished work showing that distal enhancers actually have evolved independently in a different large clade of green things that I try not to eat. And so, it may be that there are constraints about how entities operate that almost require or facilitate the evolution of certain components of them. And that's another factor that I think we're going to have to try and understand in looking at this tension between universality and contingency. And let me just close with this last quote from a wonderful book on the major evolutionary transitions by John Maynard Smith and Eero Saarenmaa in 1995, where they talk about this increase in complexity depending on a small number of major transitions, which look like they're these historically contingent events. But they raise the question about how many of these really are unique. Others have occurred several times. Then there's no reason to regard the unique transitions as the inevitable result of some general law. One can imagine that life might have gotten stuck at the prokaryotic or the protist stage of evolution. And certainly if you look at this from the perspective of a paleontologist, the globe had nothing but bacteria, broadly considered, for 2 billion years. Could have gone on for a lot longer. But I think that the reasons for accepting this claim of Maynard Smith and John Maynard Saarenmaa are probably less secure than they wrote in 1995. I'll leave it there. Thank you.